All right, welcome in everyone. This is Foundations 20, Unit 2, Lesson 6. I'm talking about solving problems using acute triangles. So in this lesson, we're not necessarily learning anything new. In Lesson 4, we learned about the sine law. In Lesson 5, we learned about the cosine law. And now in Lesson 6, we're just problem solving. So using those tools that we learned, so sine law, cosine law, as well as anything we learned in grade 10 or even previous years in that Pythagorean theorem, that's all fair game, right? That's how math works every year, sort of snowballs, builds on top of each other. Um, so, yeah, we have a lot of tools at our disposal here to help us solve situations and problems that involve triangles. So let's get this going here. The I can statement associated with this lesson says I can solve situational problems that involve angles in acute triangles. So we can use, like I said earlier, the right angle ratios. So that's your sine, cos, and tan, right? If you have a right angle, you could do sine of an angle, cos of an angle, or tan of an angle, as well as what we learned a little bit earlier this unit, the sine law and the cosine law. So we kind of have sine, cos, tan, sine law, cosine law. We've got 5 different tools here at our disposal, as well as Pythagorean theorem. So really we have 6 tools at our disposal that will help us here. Remember, these last 3 lessons, we've been dealing with acute triangles. Remember, all of these angles need to be smaller than 90 degrees. One other thing that I wanted to mention, I don't think I mentioned it in the previous videos or lessons that we've had together, but when a question says to solve a triangle, that just means find every missing side and every missing angle. So you could be given 2 sides and an angle, or 3 sides, or whatever combination. If a question asks you to solve a triangle, that just means you should have 3 sides and 3 angles at the end of it. So just thought I would throw that in there, but there's nothing new really to learn here. So let's get right to some examples. And when we're given these word problems, I like to just try to make a diagram. Like I always say, I'm not the fanciest, I'm not the best artist, but I find that making a diagram really takes this word mumble jumble that's given to us and makes sense of it visually. So let's read the example here. I like to read these questions over, right? This is, I don't know, just roughly counting 3 or 4 sentence question. I like to read it over a couple times to myself. That's what I recommend you do on a test or even right now. But let's go through it. It says 2 security cameras are mounted 6 meters above the floor, directly across from each other on opposite walls, 12 meters apart. Both cameras are pointing towards a display that is 1.5 meters above the floor. The distance from the camera on the left to the display is 4.8 meters. Draw the scenario and determine, oh, this is a word that we dealt with last year, the angle of depression for each camera. So remember, the angle of depression goes from the horizontal and measures downward, right? So from the horizontal downward is our angle of depression. So let's try to draw this out here. I'm just going to make a little box for my security cameras. I've got a little security camera right here. And let's say a security camera right here. What I know is they are on the wall. Let's make my walls red, because why not? Okay, they're both on the wall, and then they're across the floor. Right, so how far across are they? Well, first of all, they're 6 meters. I'm going to draw it just over here for a certain purpose. We're going to see that here in a little bit. They're both 6 meters above the floor. So from here all the way down to the floor is 6 meters. I know these walls are going to be 12 meters apart. right? So from there to there is 12 meters. And they're both pointing towards a display that's 1.5 meters above the floor, and it's 4.8. So this is where I might do some drawing here. This display is 4.8 meters away from the left side. So I'm going to go ahead and put my little display in here. Maybe I'll just make it a circle. So that's my display. Now the security cameras are looking down at that object. I also know, though, that this display is 1.5 meters above the floor. So if I were to go straight over horizontally each way, I have a little height right here of 1.5 meters, right? This is 1.5 meters above the floor. So that means from security camera down would be, that would be 4.5 meters. Right, the height of this little triangle here that I've made is 4.5 meters, because 4.5 plus 1.5 gives me a total height of 6. Also, what I know is if it's 12 meters across and I'm going 4.8 from the left, that means I am 7.2 away from the right. So I've really got two little triangles here made up, and I'm going to draw these over here in green. I've got one little triangle right here set up. I know this side right here is 4.5. This side right here is 4.8. And I know I have a right angle right here, right? Because the wall is going to be up and down, perpendicular to the floor. So I know I'm probably not using sine law or cosine law here. I'm probably using maybe sine, cos, or tan to find my angle. Okay. I've also got this other triangle over here on the side. This one is also 4.5 meters high. And this one is 7.2 meters across. So I've got the two triangles here. I've got all my information. This is basically, oh, I guess I should put in my, let's put in my right angle here just to remind myself. So I need to figure out the angle of depression. Remember, the angle of depression is a horizontal line and the angle going down. Maybe I'll do the angle here in blue. Remember, that angle right there is my angle of depression. If I go straight out from the horizontal, that angle down here is my angle of depression. That's my theta. So how do I find out my theta? Well, let's take a look at this. My angle theta, as you can see my mouse cursor right here, is right here. But notice that I have a pair of parallel lines right now. The floor right here, this 4.8 side, is the floor, and it's running horizontally. But also this dotted line up here is a straight horizontal line, right? Because it's the angle of depression. I know it has to be a straight horizontal line. So I know that this bottom line right here is parallel with this dotted line up here. Now, this is already kicking back to what we did in the first part of this unit. If I've got two parallel lines up there and down there, and I've got a transversal that cuts through them, that's what my hypotenuse is here. My hypotenuse is a transversal. Then this angle is going to be the same as this angle right here. They're going to be alternate interior angles. So if I find out this little angle in the bottom right of my triangle, let's indicate here, this bottom right angle here in my triangle, that angle is going to be the same size as my angle of depression due to alternate interior angles. So let's go ahead and find the measure of theta for this triangle here on the left. So compared to this angle, I've got an opposite side. I've also got an adjacent side. Opposites and adjacents are, if we remember SOHCAHTOA, opposites and adjacents are tan. So I've got tan of theta equals opposite over adjacent. Okay. So my opposite side I know is 4.5, and my adjacent side is 4.8. I just realized I don't have my calculator out. So if you don't have your calculator out right now, you should as well. Remember, if I want to find just theta, I need to go tan to the minus 1 of 4.5 over 4.8. So let's go ahead and plug that into our calculators. Remember, check your mode, make sure you're in degrees. I get an angle of depression of 43, and it doesn't give me any specifics, so I'm just going to go to one decimal place. Let's go 43.2 degrees for that first angle of elevation. I'm going to make that a little more clear that that's a degree sign. It's the best I can do. All right, same thing now on this second triangle. I've got something going on here. Once again, I see that I have a straight horizontal line right here. Remember, this would be horizontal with the ground, as well as this blue dotted line up here would be horizontal as well. That means that the top and bottom lines, once again, are parallel, meaning that this angle right down here is also going to be a alternate interior angle. They're going to be the same size. So once again, I'm looking for angle theta. So looking at this triangle here, I've got an opposite side and adjacent side. I'm still using tan. So tan of theta equals opposite over adjacent. So that means tan of theta equals, my opposite is 4.5 over 7.2. So same thing as before. Just to get theta all by itself, I need to use inverse tan, or tan to the minus 1 of 4.5 over 7.2. And if I do that in my calculator, I will get the answer. So let's go ahead and do that. And that gives me about 32 degrees spot on. So 32 degrees and 43.2 degrees are the angles of elevation of, or sorry, not the angle of elevation, the angles of depression of each camera. All right, those are our answers. Now let's throw a box around. All right, let's look at our next question here. This one here, I already am looking at it, and I see we've got maybe two different triangles going on here. So let's look at what this question is saying. This question says a man is trying to find the height of a totem pole, as shown below in the picture. Use the information to help determine the height of the totem pole. Interesting. All right, so it's a little hard to see. I don't know if I can zoom in or not. But what we are being told, I'm going to draw this just over here in this space, just a little bit bigger. But what I've got here is this first triangle is a little something like this. And this one here, that's hard to read, says that's 5 degrees. It also says that this corner right here is 40 degrees. It's 5 degrees. And then I've got another kind of triangle that's going like this. And I've got my height over here. So that's my scenario. Oh, and this side right here is 42 meters. So interesting. I don't see anything here with sine law. Or sorry, I don't see anything here with sine, cos, or tan. I don't see a right angle right now. So one thing that I can try is, like I just said, the sine law. So where might be a starting point? Well, let's see. Can I fill in any more angles? What I do see here in this diagram, if I look at the bottom right of the totem pole, I see that it's indicated I have a right angle there, which means that these two angles right here should add up to 90. Well, that little one there is 5 degrees. So that means this one here should be 85 degrees. What else do I see here before I even get started? I see this blue triangle in the bottom. I've got a 40-degree angle. I've got a 5-degree angle. So I can go 180 minus 40 minus 5 gives me 135 degrees. And I've got 135 degrees right there, which means that 135 plus whatever this angle is right here should give me 180 because it's on a straight line. So 180 minus 135 is 45 degrees. Right, and this is kind of a snowball effect. Once I found one angle, it kind of lends itself to all the other ones. So you can see here, oh, I can find this one last angle right here because I've got 85, I've got 45, and this last angle up here should add to 180 degrees. And if I do that, if I go 180 minus 85 minus 45, I will get 50 degrees, which it works, right? It's all acute angles in here, well, except for this 135, but that means we're probably not going to deal with it. So I need to find the size of H, right? This one right over here is what I'm looking for. So question I need to ask myself right now is, in this green triangle, do I know an angle side relationship? Well, yeah, I do. I've got the 50-degree angle corresponds with the 42 side length. So I can go ahead and use, if I'm looking for a side, I'm looking for H over sine of 45 because the 45-degree angle is across from H, and that equals 42 over sine of 50 degrees. All right, to get my H all by myself, I can just multiply both sides by sine 45. Okay, my sine 45s cancel out. And I'm left with h equals 42 times sine 45 divided by sine of 50. When I do the math and I cancel everything out, plug it into my calculator, I've got I get an answer of 38. And it doesn't give a specific, so I'm just going to go to one decimal place. And that would round to 38.8. I got 38.7686. And my units for this is meters. Using the sine law and a bunch of my angle relationships that I should be well versed at, I figured out the height of this totem pole. Let's get to our last question here. This one involves sort of a 3D look. Looks like we've got a triangle here on the ground and then a triangle happening vertically with that shared side from B to C. Very interesting. All right, so let's read and see what we're trying to find. It says Brendan and Diana are trying to climb a cliff. They gather the data shown below in order to estimate how high they need to climb. So we're trying to figure out the height of this cliff. We're trying to figure out from A to C. We're trying to figure out that line right there. How long is it? Let's call it H for height. So looking at, first of all, this question, I might say, hey, is this just a trick question? Do I have something that's really easy here to find H? Well, looking at the triangle that H is in, that triangle that goes from A to C to B, I see all I've got here is a right angle. I've got a 76-degree angle. And that's it. So I don't really have enough information in that first triangle to find H yet. What I do see here is that down in the flat triangle that goes from D to C to B, I've got some information there. Now, which thing might help me out here to find H, right? I'm always keeping that in the back of my mind. What can I do that's going to be useful to me? Well, if I find this side length over here, and I'm going to call it X, this side length that runs from C to B, well, then I've got in my vertical triangle, I've got an angle, H is my opposite, X is my adjacent. I can use tan to solve that. So all that I really need to get here is side X in my CDB triangle here in the bottom. Now, you might be looking at this and saying, hey, well, why can't I just use, maybe the 50-degree angle and say sine of 50 equals X over 60? Well, I'm not told here in angle C in the bottom that this is a right angle, right? Up here, I'm told that ACB makes a right angle, but I'm not told that DCB makes a right angle. So I can't make that assumption. I have to assume that it's some other angle. Let's make that a gentle curve because I cannot assume that that is 90 degrees. Maybe it's something like 80. And I can actually find that out right now, right? Because all three angles in a triangle need to add up to 180. So if I go 180 minus 50 minus 60, that's actually going to give me 70 degrees. So I've got an acute triangle here, no right angle, which means I'm either going to have to use sine law or cosine law to find side x. Here, I do not have a side angle side relationship, so I cannot use cosine law. This means I'm probably left to use sine law. Right, sine law, do I have a side angle relationship already known? Well, now I do. I've got 60 meters over here and 70 degrees over there. So I've already got a relationship of 60 meters over sine of 70 degrees equals side x, and x is opposite of the 50-degree angle. So I'm going to put in here sine of 50 degrees. So now I need to get x all by itself. So let's multiply both sides by sine 50. The sine 50s cancel out. I've got x equals sine of 50 times 60 divided by sine of 70. When I do that, I get an answer on my calculator that reads something like 48.9124, something blah, 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 blah. It's going to go on, right? Now, this is where I want us to be careful, okay? If I were just to round this off to 48.9, or even maybe a little bit worse, if I just say it's 49, I'm going to lose some precision or some accuracy. And when I go and use this x value in my next calculation, it's going to make my calculation a little bit off. So if I can use the whole number in my next calculation, I will. If not, I'm going to just round to 4 decimal places is generally my personal rule of thumb. But we've got the length of x, and like I said earlier, if I know my 76-degree angle, opposite side is h, adjacent side is x, I've got a right angle there in the corner, I can use tan. Tan theta equals opposite over adjacent. So let's go ahead and make this work. Once again, I need tan of theta. Let's fix that. So let's plug in what I know. I've got tan of 76 equals my opposite is my height. My adjacent is that 48.9124 blah, blah, blah length. And so let's try to get that h value all by itself. Well, let's go ahead and multiply this side by 48.9124 blah, blah, blah. That'll cancel out. And as well, I'll need to do it to this side. Okay, when I do this and plug in my value for h, do my calculation, I get an h value of 196. And now that I'm at my final value, I can feel free to round. It comes out to like 196.1769. I'm just going to round that to 0.2. Most of your questions will specifically say round to the nearest tenth of a meter, hundredth of a meter, whatever. I like to go to 1 decimal place if it's not specified. But yeah, that's some examples of how you can solve right angle triangles using, cosine law, sine law, Pythagorean theorem. We can use sine, cos, and tan for right angles, right? We've got all of these tools at our disposal. We actually, if you guys notice, we didn't see an example here of cosine law. Um, we've seen cosine law problems in our last lesson, which you should have just finished practice problems on. So when you're in your textbook problems, just remember that a cosine question can possibly exist. Remember, cosine law, you need side, angle, side. You need a SAS triangle, or you need a side, side, side triangle. Right? Those are the two conditions that you need to use cosine law. Otherwise, you're probably using sine law. And if you guys have kind of picked up on a trend here, a lot of times sine law is kind of the go-to, just with the way a lot of these questions are. But that's not to say cosine law is out of the question. No. Cosine law, very usable tool. So you have everything at your disposal now. Go ahead, try out these practice problems on page 147. Um, if you're having problems with them, go ahead and do more, right? This is just a suggestion of what to get you by. Um, if you feel like, hey, you know what, 4 and 5 are easy, you want to move on to more difficult ones, feel free. If you look at these and do these and say, I still don't get it, go ahead and do question 6 or 7 or number 3 or something like that, right? Do not limit yourself just to these questions. This is just a launching pad for you. So go ahead, do these practice problems. Let me know if you have any questions. And that is our lesson on solving problems with right angle triangles. Good job.